So I try to speed things up, so it's three centuries of physics on half a whiteboard. Fast forward to 2018. So basically, just to recap and give you a forward perspective, and then we'll come back to biology today. Starting with classical physics for the first 250 years of science. So they describe the motion of a moving object of mass m and the acceleration second derivative of position, and it's driven by force f. Force is negative derivative of potential. So if you know potential means the distribution and it's an energy landscape in which this massive particle exists. So you can, in principle, solve this equation for the trajectory into the future as well as in the past. Basically, you know everything about the particle. If you know the initial conditions, it's a second order ordinary differential equation in general. Although the forces may be time dependent, may also depend on the space, vary in space. But this is the crowning achievement of so-called Newtonian mechanics. And there were some more elegant, this is not elegant, it doesn't look symmetric, but there are elegant formulations of this developed by Hamilton and Lagrange. They introduced different functions, Hamiltonian, which is an energy function, Lagrangian, which is, anyway, you can look it up. I'm not going to give you a course in physics, just give you some vocabulary and concepts. So that's classical physics, which can be summarized by one word, determinism. It's a deterministic world in which classical physics exists, basically predictable and solvable analytically. Now if we move to quantum mechanics, beginning of 20th century, there were three stages of development of this theory. The first one is called first quantization or old quantum theory. Position of a particle x as a function of time is represented by a wave function. It's also a function of x, y, z, and time. It's an abstract, complex function, by the way. Complex meaning it has two components. And the evolution of a particle or system of particles described by the wave function is given by the Schrodinger equation, which replaces Newton's equations. The Schrodinger equation is the most fundamental equation in quantum mechanics. However, it has limitations too. It really works only for slow particles, slow-moving particles. For relativistic particles, and I have no time to go into details, but it's replaced by the so-called Dirac equation. So this is called relativistic quantum mechanics. In other words, here you combine quantum mechanics and the theory of relativity of Einstein. Schrodinger equation does not combine relativity. It really does not work for rapidly moving, close to the speed of light particles. There is an equivalent formulation of quantum mechanics. I'm introducing it because it's important for the future development if you want to see where physics has gone. So instead of the Schrodinger equation, where you have actually the Hamiltonian operator, which describes the energy situation for the system. And by the way, that's the same, the root of the word Hamilton, 19th century physicist from Dublin, Hamiltonian. He introduced the classical Hamiltonian. It was quantized, and it is at the center of the Schrodinger equation. Okay, so Hamiltonian is basically the kinetic energy plus the potential energy. But in quantum mechanics, these are operators. In classical mechanics, they're just normal functions like p squared over 2m is the kinetic energy in classical mechanics, and potential could be like the potential due to gravity, let's say g m divided by r squared, something like this. R actually potential, not r squared. So you can construct it like this. Now, in quantum mechanics, this becomes an operator, and in quantum mechanics, you can also construct a completely equivalent and completely sufficient description of reality, not by focusing on wave functions, but operators. And they also evolve over time. Evolution equation for the operators is called the Heisenberg equation, and this formalism is called is the Heisenberg picture. This is called the Schrodinger picture. The Schrodinger picture focuses on the wave functions. The Heisenberg picture on operators. It's actually not even that far from current applications outside of physics. I'll just mention in passing that there is growing interest in financial markets. That financial markets, we're observing some interesting phenomena in the last few days on the New York Stock Exchange. Financial markets are best described, or potentially described, by quantum wave functions. And it's an example of why would that be, for example? Because it is really, the state of the market is full of potential, but unless somebody pays real money to buy some stock, it's like a measurement problem. It is really just a wave function. It's in somebody's head, imagination. It becomes reality only when a transaction is consummated. All right? So from this point of view, you could introduce a wave function for the entire New York Stock Exchange, which would be a multi-particle wave function, just like you have many electrons in an atom or a huge number of electrons in a solid and so on. You could view the stock market the same way. And there are also applications of psychology that the human brain also operates on this kind of uncertainty principle. But I will leave it to maybe future lecturers in this course. I just want to mention in passing that this is not so crazy or abstract as one might think, because there are implementations currently going on in various fields, also in the field of genetics, where you can introduce mutations as quantum processes, largely because of the probabilistic nature. That is, things are not deterministic as in quantum mechanics, in classical mechanics, in quantum mechanics, things are probabilistic. All right, so first quantization, wave function. Second quantization, I haven't talked about. Second quantization springs from the fact that you can rewrite the entire textbook of quantum mechanics in terms of operators, not wave functions, and the basic properties are operators. And in particular, these operators, called creation and annihilation operators, are introduced, and they are basically operations on quantum systems. Let's say, I'll give you a very simple example of what the creation operator and an annihilation operator mean. Let's say this is a potential well. In other words, like a confining potential for a quantum particle. Let's say an electron sits here in this potential. It's in the ground state. This is 0, ground state. This is the first excited state, the second excited state, and there could be many more excited states. A creation operator will act on this electron and put it in the first excited state. So it has to give, like a photon would be physical representation of this. You have to give an energy kick for the electron to jump to the next level. It also, sometimes these are referred to as ladder operators. As you can see, this is becoming a ladder, and very typical for quantum systems. In classical systems, you don't have such behaviors. So creation, annihilation, ladder operators. Because you climb the ladder, and you can climb down the ladder, and then you have an annihilation operator. It doesn't really annihilate the particle, it simply annihilates the excited state by 1, or lowers the energy, also called lowering and rising operators, different terminologies. Anyway, these are the relevant operators, and you can actually very quickly connect this to the stock market, because in stock market you also can go up and down in price, and one could introduce these kinds of operators to describe the dynamics of the stock exchange. All right. The next step in the development of quantum physics was third quantization. So you go from these operators to quantum fields. Now, if you have lots of particles, like in a solid, in a metal, you have a lot of electrons, not one or two, but you have, macroscopic number, 10 to the 23rd of electrons or something like this, 10 to the 18th, huge numbers. So instead of that, you introduce quantum fields, quantum field operators, and you have a quantum creation operator. So this will be a Fourier transform on these ladder operators, which means this kind of transformation, and introduce wave numbers. There's a bit of detail I will skip because then I get bogged down and we never finish. We never get to biology. But I'm just giving you the lingo and very quick introductions what they mean. So that becomes now space and time dependent. So these operators describe the dynamics of energy transformations. Okay, and that leads to something called the quantum field theory, which is very sophisticated. Although it's not that recent, the quantum field theory was built in the 1970s, 60s, and 70s. And again, lots of Nobel Prizes were given for quantum field theory and quantum electrodynamics, which is its representation for electromagnetic fields. One of the most famous people, an American physicist called Richard Feynman. You may have seen some popular books. Surely You're Joking, Mr. Feynman, I think, or Dr. Feynman, I remember the title. But anyway, he was a very interesting character, and most of these people were very interesting characters, but that's probably for a popular book in the future, another course. So quantum electrodynamics, Julian Schwinger and others. And finally, when you introduce elementary particles and introduce special quantum states of these particles, you create something called the standard model. Standard model basically is the theory of everything up to now in physics. Standard model. It's beautifully symmetric, and it's almost complete because the only thing missing from the standard model is gravity. The force of gravity and quantization so far cannot mesh. Nobody has come up with. This was actually one of the quests of Albert Einstein to create a theory of everything, and unified field theory is another. So sometimes you'll see these terms, the theory of everything, TOE or TOE. That would mean a unification of all physical forces under one umbrella, conceptual umbrella, or grand unified theory. Grand unified. Somehow we always come back to biology, a toe and a gut. Okay, so that's where this is roughly now where we stand with the Higgs particle being discovered and confirmed. The standard model is more or less in a confirmed shape. What happened in the intervening years within the expansion of quantum science throughout physics and beyond, the first step was to go from atoms to molecules, to describe molecular vibrations and rotations and electronic states using the quantum physics principles, quantization of vibrational states. That led to spectroscopy, which I mentioned. Now we can use these as fingerprints for the particular frequencies or wavelengths, if you will, of electromagnetic radiation that molecules absorb or emit. And that is related to a chemical structure. You can relate it one-to-one, basically, and detect tiny, minute quantities of particles, of molecules in a larger sample. You can also conclude about the composition of distant stars just by looking at the spectral fingerprints of light coming from these stars. You'll detect signatures of helium, hydrogen, and other atoms, right? That's how you get it from quantum mechanics. Just by analyzing what amount of energy is needed to go from one level to the next. This is, in this particular case, it's very simple. They're all equal. But of course, if you have a molecule, even water, there will be a lot of different degrees of freedom. It'll be rotational degrees of freedom, vibrational degrees of freedom, electronic degrees of freedom, each of which have a different frequencies, and you can recognize these. So therefore, you can conclude, okay, there's water on Mars or something. Or Mars would be too simple because you can probably observe it with a satellite, but on some distant exoplanet somewhere. Okay. So atomic physics, then molecular physics, or now we're coming to chemistry. And chemistry talks about bonds, atoms making molecules, and therefore bonds are being made. And you can use spectroscopy to understand chemical reactions. So quantum chemistry is a natural extension. It was built in the 40s and 50s. And you replace the sort of Lego representation of molecules in chemical reactions by electronic density states, right? So instead of this ball and stick representation for a molecule, you suddenly draw distribution of the electronic cloud for the molecule. And that is related to the wave function. The square of the wave function is the probability density of the electronic cloud. So electrons are no longer seen as tiny little ping pong balls, but instead as clouds, which spread in space and can move in time. Okay, so that's kind of easy to grasp. But when you go into something like a solid, then suddenly you say, well, where is quantum? What is quantum? What's going on? And even Einstein made this only mistake to my understanding. Well, actually, he never believed in quantum mechanics, by the way, but he didn't make any mistake. It was just an opinion. You may know this quote from Einstein. He said, God doesn't play dice. In other words, he was I don't know if he was actually an atheist, I think, most of his life. Maybe eventually he started believing towards the end of his life, but he believed in some sort of divine principle of the universe. Something must be very beautiful and symmetric, and therefore probabilistic or stochastic representation of the universe would be kind of ugly and not believable. So it's like playing dice, you know, with every molecule you play dice. Maybe it's here, maybe it's there, I don't know. And therefore Einstein didn't like that. But he also developed many other things, and one of which is the theory of solids, the Einstein theory of solids. So a solid, and we're kind of coming closer and closer to biology, but inching very slowly. But cells are not solids, of course, but they are not liquids either. And that's one of the problems of biology, and we'll come to the questions about this in a second. But in the simplest representation, a solid is represented as a lattice, regular lattice, crystal lattice, where you have atoms in regular positions, you know, in 3D. I'm just drawing a 2D cartoon of it. Masses, identical masses, which are connected by some bonds. That's why there is a solid. Otherwise, it would be a gas or a liquid. A solid, and it's represented by, as I said, masses and characteristic average distances between these masses. These are called lattice constants, A, B, in the two directions, Y and X, right? And there is a third direction, of course, I'm not drawing, but you can easily guess and see. And so in classical physics, you would say, well, okay, that's it, you know. There's the potential. If you squeeze it, it'll resist it because there is a force, restoring force. But in quantum mechanics, nothing is ever static. Even the ground state, you know, which I represented here, the zero energy state, you cannot go below. There is something called the ground state. That's the lowest energy state. Every system in quantum mechanics has the lowest energy state. You cannot go below it. But even that state has characteristic frequency called omega 0. And even at 0 temperature, there is a quantum oscillation going on, costing you no energy. It is really what it is. Every system has this ground state which is vibrating. But so here also, a crystal lattice is not is not static. It is, these atoms are oscillating around their equilibrium positions all the time. There's no such thing. Tiny oscillations, mind you, but still never stopping. And so here's now the quantum theory of solids. You assume these distances, you assume the masses, and now you allow the oscillations. And the question is, are these oscillations in any way synchronized or not? And Einstein assumed that they are not. Basically, he made a theory of gases for solids. Because for gases, all these atoms oscillate independently because they don't interact, right? But once you have a solid, they are bound by chemical forces to be, on average, this distance away. But on average, all the time they are moving. And so Einstein introduced this gas representation where frequencies are arbitrary for each of these masses or atoms or molecules making a solid. Paul Debye came along and corrected Einstein, introduced something called wavelength. So in other words, these masses oscillate together and they're in concert. And instead of looking at each mass individually, Paul Debye introduced collective, and it's a very technical term, by the way. It sounds like communism, right? Collective, or maybe rock music, a collective, some kind of, right? I've heard some bands called collective, or jazz maybe. Somebody's collective. Collective modes. Well, it is in a way Marxist because these atoms are bound together and they have to move together. So one moves to the right, and then it's like a domino. The next has to. So collective modes of vibration. Collective modes. Okay, so this is the basis of Debye's theory of solids, and he was able to explain these very precise observations that specific heat of solids means how much heat you have to deliver to a solid to raise its temperature by a given amount. C is the specific heat per mole, and T is the temperature, absolute temperature in Kelvin. And this was a pesky, very pesky fact that low temperatures, specific heats of solids depended on temperature to the third power. And Einstein couldn't get it. It's hard to believe, but that's true. Had he got it, he would have won a Nobel Prize, which he did one, but second Nobel Prize. So Paul Debye got it. And so Einstein's prediction was this. He got this result. A specific heat of solid at low temperature goes like this complicated exponential polynomial mixture function. And Debye, I'm saying this actually for a reason, because last time I told you that there are some very strong similarities between physics about 100 years ago and biology today. This is one of those similarities. The other one was the photoelectric effect, right? The photoelectric effect, remember, means photons striking a metal and causing, if they have enough energy, they will cause a current to flow. This specific heat of solids is a second. And by the way, this was comparable or somehow metaphorically similar to photosynthesis. I'm going to write this down because it's sufficiently important. So physics says, okay, there is a photoelectric effect, which is a quantum effect. We actually enjoy it in washrooms, right? You don't have to touch the tap. You wave your hands. It's actually irritating. Sometimes it never works. I wave and wave, and different area, nothing happens. But anyway, it should in principle. The photoelectric effect is a result of light striking a metal and ejecting an electron if it has enough energy. The photosynthesis effect in biology is something like similar to it. You have a quantum of light, and you have we'll see this complicated molecules of chlorophyll, and the electron is ejected, but not from the surface. It's actually delocalized, and its energy is collected through a funnel in the collection or electron reaction center, in the reaction center. So the principle is very simple and similar to physics. So this is the number one similarity. This is number two, as you will see. In physics, we have this collective oscillations of solids. Lead to a prediction that specific heat of solids varies like the cubic power of temperature. As you will see in living systems, temperature actually doesn't play a major role, except for you have to have a sufficient, well, first of all, most of the organisms we are familiar with are stable. They maintain the same temperature, so you don't vary it like a knob in physics. You maintain, it's homeostasis. We'll come back to it in a second. But something else is very important, which is time. And I will come back to this, but just want to highlight to you that this is similar. I don't know if you can see it. Come back to it in a second. Let me actually jump because I put it in out of order a little bit. Okay. Okay, so in terms of metabolism, there are two major, and you probably know it better than me if you took biochemistry, two major ways of producing energy, actually, including photosynthesis will be three. But in non-plant cells, mammalian cells, animal cells use either glycolysis or oxidative phosphorylation. Oxidative phosphorylation is a very complicated 25 or 6-step cascade of reactions which converts glucose molecules into ATP molecules, which is the currency of energy in almost all biological systems. And what's important in this is the electron transport chain, where electrons, as the proton pumps are activated, the electrons are released and they hop between these 5 complexes in the inner mitochondrial membrane, complex 1, 2, 3, 4, 5. And this hopping, by the way, is a quantum process. It is a quantum tunneling, one of those crazy things that I talked about, and there are some papers demonstrating this. But that is maybe incidental, maybe not so very important, but it is a fact. So the pathway is complicated, and part of it is glycolytic pathway, and then you have the citric acid cycle and oxphos at the end. So you transfer high energy electrons to low energy electron states, and as a result you produce ATP, which can be used for many processes. Almost all living functions require either ATP or GTP, and okay, and that's the connection. It's energy, just like heat in solids is energy that is delivered to the solid in order to vibrate, and then these vibrations or molecular collisions determine the temperature. So you find out how much heat needs to be delivered per mass to raise the temperature. Now, if you jump to biology, there's nothing like this seemingly, but there is something very interesting and somewhat reminiscent. Namely, you have time, cycle time. How much time is needed to cycle one glucose molecule through the system and produce ATP. But out of curiosity, there are some trivia that maybe are worth throwing into the mix. One of which is, do you know how much ATP is produced by the human body during one day? Wild guess. Oh, another question. How much calorie, what is our, on average, how many calories do we consume? Of course, it varies somewhat, but all right. Roughly?
1,500.
How much?
1,500.
For people like, yeah, you, maybe I probably eat more. But yes, 1,500, 2,000, 2,400. I think if you're really hungry, maybe 3,000 calories. But these are calories, actually, like, not physical calories. These are nutritional calories, right? And you know that there's a difference. Nutritional calories are 1,000 physical calories. So it's really 3 million calories, but you know, a physical unit for energy. So let's say 2,000 calories. Calories with a capital C because they are bigger. So that means 2 million calories with a small c, physical calorie. And 1 calorie is 4.2 joules. A joule is a unit of energy in physics, which is kilogram meter squared per second squared. So our consumption, we require something like 8.4 million joules a day. Okay, so what? It's a number. But if you convert this into per second, because a day is 24 hours, an hour is 60 minutes, 60 minutes, 60 seconds, and you then find out what is the power. Power is energy divided by time, right? How much energy is consumed in a unit of time. And in physics, the unit of power is watt, 1 watt. W-A-T-T. Following James Watt was the heat engine guy in England. And so 1 watt is 1 joule per second. If you do the calculation based on the calories and convert 24 hours into seconds, it turns out, and this is kind of an easy to remember result, that on average one human being produces the power of, now is your guess. Can you relate any sort of units of power to anything? Electrical bulbs. If you go to Home Depot and want to replace a bulb, what are you looking for? The rating on the bulb, typically. 60 watts? Yeah, that's an average. Could be 40, which is weak. 100 would be probably, sometimes you have 300 for these big, not chandeliers, but standing lamps from 19th century. But 100 is a big one. So a human being, like you or me, on average, consumes 100 watts. So we are producing as much energy in one solid bulb. This actually will come back on Thursday, which is an amazing commentary on not on the efficiency of the human body, which is already quite impressive, right? Because you wouldn't expect that the amount of energy that powers one bulb is enough to power you. Would you think that? Or is this surprising at all? To me, it was surprising. Because we do so much, right? Not only mechanically, but also in terms of our brain, which is quite amazing in its own right. And by the way, 25% of this goes to power the brain. So our brain is almost like a tiny flashlight, 25 watts, less than the lowest rating of the bulb. 40 watts is the lowest, I think. Maybe now you can get 30 watts to save energy. The brain uses 25 watts on average. And most of it, by the way, uses for maintaining the temperature and protein synthesis. Only about 3 to 5% of this, which will be something like 1 watt, maybe 2 or 3, for cognition. So it's either we're not using a lot of our brain for cognition, or our brain is super duper efficient. Okay, so that's I'll leave you with this. We'll come back to it on Thursday, because this number is amazing, and actually can be converted in some other numbers. But what I wanted to bring to the discussion is metabolism, which is energy production or transduction, because we convert one form of energy into another. The energy of the biochemical bonds and nutrients into the ATP. So ATP energy is really electrostatic energy of the phosphate bond. ATP converts by hydrolysis to ADP, and that releases something like, we'll see, I think it's 60 to 80 kilocalories per mole, something on this order per bond. But I asked you a question you didn't answer. We got this. The question was, how many molecules of ATP do we convert, or what's the turnover of ATP? Because it's really, we don't make them from scratch. It's back to ADP, from ADP to ATP, and you know, in a circle. So how many, or how many molecules of ATP are converted during one day by a human body? No? Well, it's the equivalent of our weight, actually, body weight. So if your weight is 70 or 65 kilograms, that's roughly the amount of the mass of ATP conversion going on in your body during that day. So if you want to remember two things from today's class, is we are like a bulb, energetically speaking, from the physics point of view, and we make and from biochemistry point of view, we make as many. The mass of the ATP molecules we convert during the day is equal to our mass. So we need to eat. But that leads to something quite profound. Namely, this is a result that has been a bit of a mystery for two centuries. More than that, actually, going back to some very famous people, Lavoisier and Laplace, a famous chemist and a famous mathematician, physicist. And then other people like Rubner and Kleiber, especially Kleiber, he classified various species, they did the measurements, assembled all of this. And they discovered something very interesting, which is that for almost all species, there is an interesting scaling law, which is called the allometric scaling law. Which says that the power generated by a living organism of weight W scales not linearly with the weight. It scales with exponent beta. And exponent beta in most cases is 3/4. And there are some exceptions. In plants, it can be 1. In some other animals, microorganisms could be 1/2. But by and large, maybe 90% of the cases can be identified as 3/4 exponent, which means that if you, let's say, compare the energy demands of a growing human, they will not increase linearly. If you double in size, you don't need to eat twice as much. Only 2 to the power 3/4. Maybe I don't remember what it is, but if it's I can tell you what it would be if you increase in size 16 times. So from a toddler, 5 kilogram, maybe a baby, 5 kilogram baby, right? 10 pounds, a baby, to an 80 kilogram hefty guy, 16 times, right? From 5 kilograms to 80 kilograms. That's 16 times. Right? 16 is 2 to the power 4. So you don't have to feed the big guy 16 times the amount of calories that the baby gets. It's enough to feed 8 times. I don't know what the baby, how much baby needs to eat, but anyway, you get the picture. So this is kind of interesting, but actually there are very important implications of this. For example, one of the implications is how do you scale? You may be interested in the field of pharmacology or medicine. If you do clinical trials, clinical trials, new drugs being developed, you test first on cells, right? Cell lines, cell culture. Then you go into small animal, rodents. You do mice and then rats and eventually dogs, or sometimes monkeys. And then you go to humans. And how do you figure out the dose? If you go from animal to animal, mice are like 20 grams in weight, rats 200. So you increase 10 times. And you very quickly discover that this is the law that you should obey because it's metabolism. These drugs are metabolized. And therefore, it's very important because if you extend it linearly and you went from a dog that weighs, let's say, 20 kilograms to a human that weighs 80, and you give 4 times the dog dose, you could kill that person. And in pharmacology, as you may know, quite often you determine something which is called the maximally tolerated dose, MTD. And especially in diseases like cancer, you want to crank up the dose up to the maximally tolerated dose to kill cancer cells effectively and quickly. If you don't, sometimes it actually is provoking the malignancy rather than removing it. So anyway, back to the reason I brought this up. Allometric scaling laws, 3/4. And I'm going to put it next to it. It's completely mathematically analogous to the Debye scaling law for physical objects. This is specific heat of a solid. It requires a temperature increase with the third power of its absolute value for metabolic rates of biological systems. You roughly, in most cases, I put this 3/4. So the mathematics behind, I don't have the time to go through, but it's absolutely identical to the way it is derived in the physics of solids. In other words, so-called Debye theory of solids. It's actually, I'm going to show you something. And this was published and is credited to a person called Lloyd Demetrius. You can look him up. He's a Harvard, Göttingen, Max Planck Institute scientist, and he wrote papers demonstrating it. I think I do have maybe some. Here it is. The correspondence between the Debye theory of solids, which introduces the Planck distribution of energy, and the energy is in terms of the waves. And you do the integration over the frequency of these waves, and you get the exponent. There is a generalization of it, which is kind of interesting and important to put in, because actually, when you do the math, you gain some insight. It says that the scaling law actually is given in terms of the dimensionality of the biological system in terms of enzymatic reactors. So let's say mitochondria, distribution of mitochondria in a tissue or organ. Of course, in most cases, it's three-dimensional. We are three-dimensional. We exist in all three, although it's not quite isotropic. But if d equals 3, then you get 3/4. 3 divided by 3 plus 1, 3/4, right? If d equals 2, it's 2/3. 2/3 would be flat. So largely flat surfaces. So for plants would be 2/3. And if d equals 1, so if you had a very linear biological, of course it's, I don't know, I don't have too many examples of linear objects in biology. There might be some. Then you would have 1/2 exponent. So and there is also an explanation in Demetrius's theory for this exponent 1, which is isometry or linear, and actually it applies to something which is the classical regime of the quantum oscillators. And I sent you to the source if you're interested, because it's really quite beautiful how we can use mathematics to explain complex biology. But interestingly, you can also do some explanations. So this whole quantum metabolism theory relies on the fact that there is synchronization throughout the organism. So metabolic synchronization, and now it's actually becoming very, very hot. You may know the Nobel Prize in Medicine and Physiology from 2017 was given to 3 scientists for the discovery of biological clocks, molecules that synchronize the cycles, including metabolic cycles. So synchronization throughout the body is implicit in this theory. If synchronization is lost, then you go back to this linear scale. This becomes linear, and actually it's a reflection of inefficiency. Biological systems are organized hierarchically, and these are interlocking hierarchies from protein systems to cell systems to tissues to organisms, which all communicate from the bottom up and top down, and that has to be synchronized. So synchronization, when synchronization is lost due to various reasons, you lose the efficiency of the system as well. And losing efficiency is also represented by increased power consumption. Just like societies, you can think of a well-oiled society, like let's say Canada or Switzerland or other developed countries. There's not much loss. Call it corruption. Loss, corruption, finance. So you can put a lot of resources into a society, but when it's corrupt, there is no effect because it's basically stolen or distributed, and there is no benefit to society. The same thing for biological systems. And one example where this is lost and this scaling law changes is cancer. Cancer is a society of rebel cells, individuals. They don't coordinate their activities. They don't contribute anything to the body. They simply are drained on the resources. In fact, outcompete normal cells typically for resources, but they are inefficient. They turn to glycolysis, produce a lot of lactic acid, etc., etc. I don't want to go into oncology, but it's an example of this loss of efficiency through desynchronization. The same goes for cell division, etc. So I just wanted to emphasize these two similarities. I hope that there is something of that resonating with you. Photoelectric effect is similar to photosynthesis. Oscillators in solids are similar to metabolic oscillators in living systems. Synchronization is like quantization, and you can see it in the allometric scaling laws. There is an explanation why this is 3 and this is 3/4, but I'm afraid for lack of time I just send you to the work of Dr. Demetrius. But the mathematical model is completely analogous. Okay, so that's the empirical explanation of the allometric scaling laws. 2 centuries of biologists, physiologists collecting data, and now an explanation of this from a higher perspective. So let's go back to, because I had to jump a lot of slides to connect it. Okay. All right. So, quantum physics, elementary particles, quantum chemistry, solid state, large objects. This is an example of a quantum effect occurring in a macroscopic object. It's true for crystals, it's true for any kind of solid. You could measure the specific heat of this table and you'll be able to fit it to this formula. I guarantee you that. It's coming from quantum mechanics. So it's in a way, it's a reflection of deeper reality. But there are also other examples of quantum effects at the macroscopic scale. Because you may have, even if you took quantum mechanics, you probably only learned about application to electrons, neutrons, protons, tiny little things you can't even see. But these are 5 examples of macroscopic quantum phenomena in physics. I mentioned this, crystal vibrations of, this gives rise, I forgot to mention this. These collective oscillations in solids are called phonons. Phonons, right? Phonons, and you have photons. Okay, photons are electromagnetic quanta of light. Photons, phonons, are quanta of vibrations. So we have phonons in solids, but we also have, I mentioned to you earlier, magnetism. Ferromagnets, magnets you can buy at the toy store, are macroscopic quantum phenomena. And in magnets also you have waves of spin. They're called, these spins, and they are called magnons. So magnons are quantum excitation waves, collective waves of magnetic properties, or magnetics, in this case, dipoles or spins. Superfluids, it's a bit less well known. Superfluids are helium-3, helium-4 at very low temperatures. There's a fluid that becomes, in a very strange way, has no viscosity. If you stir a vortex in that fluid, it'll never stop. And there were experiments. This will go on, will keep on rotating for 3-4 years, for as long as the experiment was going on. So superfluidity is a quantum phenomenon. It's an example of a condensate, it's called Bose-Einstein condensation. Very interesting because it's a macroscopic transition to the ground state. And in this case, ground state is a superfluid. Superconductivity you may have heard about. Superconductors are, first were metals, now they are ceramics. Groups of materials which have no electrical resistance. They conduct current with no resistance. We are surrounded by electronics. All of this consumes energy, as you know, and a lot of energy losses, especially in transmission lines, are due to the resistance of the transmission lines, and a lot of dissipated heat takes place. But in superconductors, currents cause no dissipation. There's no loss of energy. These are special materials. The caveats here, in these two cases, superconductivity and superfluidity, is yes, they are macroscopic. That is, you can make a big superconductor. However, they require low temperatures to avoid these losses. And for superfluids, the temperatures are extremely low, like minus 270 Kelvin, Celsius, or 3 Kelvin. For superconductors, I don't know what the current record is, but the last I checked was something like 160 Kelvin, which is minus 100 degrees Celsius, minus 110. So that, of course, would eliminate them from immediately being suspected of doing anything in biological systems, because we have to take into account room temperature or physiological temperature, which is even higher, 36.6 Celsius. So there are no superconductors known to anybody currently that would operate at this temperature. Superfluids, no. But this, yes. Laser action. Laser pointers, I don't know if we have any here, but of course you're familiar with laser pointers. This is a very special quantum phenomenon. lasers. So lasers are basically pumped to systems which are energetically pumped to an excited state, and they spontaneously emit radiation at a predetermined frequency, which corresponds to the energy gap, and it's coherent. That means all the photons have the same frequency, and they are in phase. So it's like a perfect wave. As opposed to white light. White light has a spectrum. All the electromagnetic, all the wavelength in the visible spectrum from 400 to 750 nanometers are represented. They kind of average out and you see white light. Laser has a single, it's monochromatic, right? Red or blue or sometimes green, because it's tuned. I lost. There was a diagram of this. Oh, here. To this energy gap, so delta epsilon, which is h times nu frequency, and speed of light. So it's what is this, hc over lambda, I think. So the wavelength is given by the energy difference, and that is fixed, 1. So laser is a quantum phenomena that you can use. Maybe you can buy a laser at dollar store for $1, $2, and play with a quantum system. But one thing I want to mention is it's different from the other ones. That is, you require energy pumping. It's not something that happens spontaneously. It has to be engineered and then pumped energetically. You have to deliver power to it. Which, however, brings us closer to biology, because, as you know, in biology, we need to pump the system with nutritional energy and so on. So now it brings us to the question of quantum mechanics and life. So we have seen that there is quantum mechanics operates in molecules, in large systems like solids. There are not too many examples where it operates at both large temperature scales and size scales, but it's not excluded. However, we don't have too many examples of quantum mechanics operating in a wet environment. This is one problem. Humans and most living systems are composed of about 70% of water, right? So that's one of the major criticisms. However, okay, so this is an argument against this skepticism that nature had 2 billion years of experimentation on this planet with many, many replicas, and natural selection operating to accept and advance and improve and refine solutions which work. Right? So quantum mechanics is, as we can attest from these examples in physics, a very useful advance, conceptual. And why should we be so arrogant and say that we are smarter than Mother Nature? We came up with quantum mechanics, but Mother Nature took 2 billion years and was silly enough not to stumble upon it. So there are some very interesting features of quantum systems that might be useful in biology. And laser is an example of coherence. And I mentioned to you through these metabolic laws that coherence at the organismic scale is very useful to have. I mean, we definitely are unitary as an organism, although composed of very many different parts, seemingly disjointed, but there is communication going on from one organ to the next, and you can, there's many systems that interact at the same time. How does it happen? There is no, overriding simple principle to say this is how it's all integrated. We just explore one piece at a time of this puzzle, and then we understand individually, but not globally, how we operate as an integrated entity. I'm not going to get into the quantum entanglement, but you will find in the popular literature a lot of speculation that quantum mechanics explains some strange psychological phenomena, including, there's actually a very interesting book by, I think his name is Fred Wolf, called The Dreaming Universe, and it claims that in the world of dreams, our brain turns into the quantum operating machine, if you will, or computer. Now, without going into, I wouldn't call it crackpot, but speculative science, let's put it this way. There are some real gifts of quantum mechanics that can explain a lot of things. One of which is, in classical mechanics, if you accepted quantum mechanics, you couldn't even make atoms, because electrons and protons have opposite charges. They would basically cancel each other out, and the electron would fall on the nucleus, and there would be no atoms, no sizes, no molecules. The second thing is countability. That is, you can create, just like in biology, you create the entire, the entire complexity of biological systems from a very small number of building blocks. In physics also, you have elementary particles forming the standard model and subatomic particles, and that's it. And from this you can move on. In biology, you have nucleic acids, amino acids, phospholipids. It's a small number, countable number of elements, and you can start building, like from Lego, the entire structure. This is the most interesting and the most recent addition to this menu of gifts. You may have heard about quantum computing, and maybe somebody spoke about quantum computing in this course. No? But quantum computing is all the rage. You know that Google is working on quantum computers, and there was no, you don't know? Oh, there was actually a company based in Vancouver called D-Wave. No? All right. So Google bought D-Wave, and this company made the first quantum computer. That is, what's the difference between classical computing and quantum computing? Well, major. In classical computing, you have bits, right? Bits are strings of zeros and ones. That's how computers operate. And specifically in physics, again, it's quantum mechanics because you have electronics. Zero is no flow of current. One typically is current flowing. So you have switches basically, and you build up these codes. Or store, you can store in the memory a pattern in terms of the microchips and the elements conducting current. Now, so that's nice. And we'll come to it probably at the end of this lecture, what limitations we have with this kind of computing. So classical computing is based on bits. Now, quantum computing takes you to a different planet altogether. Because in quantum computing, you replace a bit, so you have only two possibilities, right? 0 and 1. 0 or 1. In quantum computing, you replace a bit, so it's one bit of information, two possibilities. You can think up or down. But in quantum computing, this is replaced by a vector with unit length. So unit vector is actually a wave function which has a length of 1, but has a phase of from 0 to 2 pi. So it has an infinity, really an infinity of orientations. So you see, a bit is only this or that, up or down. A qubit is this entire sphere. This vector can now rotate all over. And furthermore, in quantum computing, so in classical computing, another advantage is, of course, this is the primary advantage. But the second advantage is in classical computing, if you are, for example, you're searching for the shortest path between point A and point B, right? So Google Maps, let's say. I want to go from the U of A to the Southgate Shopping Center or something like that. So you would explore all the possible pathways one by one, right? The computer will go this, okay, this is the shortest. At the end, all possibilities exhausted. It's a serial computing in series. And you have to explore all of this separately, and then you scrutinize it, rank it, and that's it. You get the ranking, right? Yeah. The same if you go to Expedia, you try to find the cheapest ticket for a flight to Toronto or something. But in quantum computing, you send a wave function, and the wave function is everywhere at the same time. Explores all. So you remember, in quantum physics, you don't have this or that. It could be this and that, and that, and something else. All the possibilities are represented by a single wave function, and then you find out where is the highest amplitude of the wave function. It's just like these two slits, the double slit experiment, remember too? So if it was a classical mechanics and you had a electron, like a ping pong ball, electron goes here or here. In quantum mechanics, you may have a million slits. It'll go everywhere. And then we'll reconstitute the screen and it'll show you where is the diffraction pattern. This is the same thing. This is a quantum search algorithm, which allows you to send the wave function everywhere at the same time. So the time scale is reduced enormously, exponentially reduced. So the power of this computer is incredible. Okay, so you can store information by quantum qubits by quantum mechanics. You can also do information processing by quantum search algorithms. And then you can build complexity and emergence. Okay, so a little bit of self-criticism. Physicists like to reduce everything to physics. Obviously, it's a little bit arrogant and probably stupid. But we have to give it to physics that actually has been able to explain a lot of phenomena. And we still have some difficulty with biology, but maybe quantum effects can be somewhat, well, fill some major gaps in knowledge. So instead of maybe informing other fields, historically we've actually had a hierarchical organization of knowledge and very little flow of information between fields. So it's this silo mentality, I guess, of scientists, where people work in, even within my department of physics, you have specialists on elementary particle physics with so-called focus group. Then we have condensed matter physics, another focus group. Then you have geophysicists and astrophysicists somewhere else. But for our purposes, chemistry, biochemistry, then you have cell biology, and then physiology, and people stay within this group. And the only thing that these lines indicate, that the only thing that goes between fields is some of the most rudimentary aspects. For example, physics, elementary particle physics, only gives electrons and protons to the solids, to condensed matter physics source. And from physics to chemistry, well, you forget, most of the time you forget about electrons except for bond making. Everything else is almost Lego blocks from atoms you build, or ions, you build molecules and so on. For biochemistry, you forget most of chemistry except for the nucleic acids, amino acids, and so on. So this is one of the problems with these kinds of ideas that we're talking about here. And this is the explanation why this is happening, actually. The explanation, you have to go out and you can take your markers. Well, otherwise they will steal them. So maybe you should take them, bring them back on Thursday. Thank you. So this is the last slide probably for today, because it really explains the compartmentalization of science. So the combinatorial barrier or computational barrier, what is this? This actually explains why fields of science are created in the first place. Because you may think that chemistry is simple. In chemistry, you have 16 elements or something like this. That's all you have. But the number of molecules you can combine from 116 elements, let alone 116, take the most basic 20 or so, is staggering. And how staggering, we'll come to it in a second. The same goes for any other field of human intellectual activity, because it's not the number of elements you play with, but the number of combinations you can create from these elements. So I'll give you one example. Sorry, I don't have a marker now, but you can, the number of amino acids is one example I'm going to give you, forming a protein, right? So you know how proteins are made, peptide chains which fold and make a protein. Now, as average size protein will have, what, 400, 500 amino acids, a globular protein, right? Something like this, 500, let's say, for the sake of argument. How many amino acids are there in nature? 20. Okay. So you have 20 to the power 500 possibilities of making proteins with length 500. Not all of them have been exhausted by Mother Nature, and probably never will be. And the answer is on this slide. And for us, of course, it creates a field of protein biochemistry. This is called Alsacer's immense number. It's a technical term. 10 to the power 110. So it's 1 and 110 zeros. Why is this important? Because it's an absolute barrier, at least as far as classical computation. Quantum computation, I don't know if this applies to, but let's stay with the classical computation. An absolute barrier to even inspect, let alone do any operations on this set. Why is that? Because this number is the product of the size of the universe measured in number of protons and the time of the universe measured in transitions between quantum states. So if each proton had, let's say, 2 states, it could be up or spin down. The mass of the universe, I think, is 10 to the 70th. I didn't write it down. Proton masses. The age of the universe, you may remember, is 16.5 billion years, which translated to picoseconds, because a picosecond, 10 to the minus 12, is the time to make one transition for the spin of a proton, up, down. So the age of the universe is 10 to the 40th picoseconds. If you multiply it, this would be the absolute limit on the size of a set that the entire universe operating for the age of the universe as a single computer would take to inspect a set composed of 10 to the 110 elements. Okay, you get it? That means that's the absolute maximum you can, the entire universe being a supercomputer operating for the entire age of the universe. That set is huge, but it's smaller than, as I showed you, the set of possible proteins, even only 500 amino acid long. You can have proteins which have 1,200 amino acids. I know a few. The same for genes. A gene, so we have 25,000 genes, I think. A gene may have, well, a few thousand nucleic acids, right? 4 possibilities of the nucleic acids and coding into a gene. So in the codon, so it's 4 to the power 3,000, let's say. It's huger. It's many orders of magnitude greater than this number. So the number of potential genes, or even take one gene and genetic mutations in one gene, is impossible for us to grasp. And therefore, you create a field of genetics, because you have to create in this field, not just understand the elements with which you play, but also the relationships, and you have to create shortcuts. There is no brute force approach, just going one by one. I'm going to check every possible gene, every possible mutation. Forget it. It's impossible. The same with somebody writing a grant proposal and promising to create computer models of all the proteins of a given size, and then finding out what kind of mutations can lead to misfolding assembly. Impossible, right? Okay, so that's basically all I wanted to say today. And on Thursday, we'll come back to the issue of the brain and where quantum phenomena may shed some light on neuroscience. Okay, thank you.